Okay, we're now going to talk about how to find the mean and the standard deviation for a binomial distribution. So in a previous video, we talked about how to find the mean and the standard deviation for any discrete distribution. But the good news is the formulas for a binomial distribution are actually much simpler. The other formulas would give us the same answer, but we can get it much quicker. So for the binomial distribution, we always know our n and our p. So how many trials and the probability of success. And the mean is just n times p. And the standard deviation is the square root of n times p times q. And remember that q is always 1 minus p. So back in an earlier chapter, we learned about the range rule, so what we consider minimum usual values and maximum. So remember, the minimum usual value was the mean minus 2 standard deviations, and the maximum usual value was the mean plus 2 standard deviations. Okay, so let's actually use this. So this is a problem that would normally be done in class, so we're going to have to kind of make up some numbers, but that's okay. So it tells us that 10% of the general population is left-handed. So if we're talking about if a person is going to be left-handed, that'll give us a p of 0.10. Okay, so let's just say we have 26 people in our class. I'm going to assume that it's a random collection of people so that the trials are independent and everything. So our n here is going to be 26. Our probability of being left-handed was 0.10, which makes our q 1 minus 0.10, or 0.9. Okay, how does this suggest a binomial probability distribution? So our number of trials would be the number of people in the class. So So 26. Either the person is left-handed or not, so those are our two outcomes. Since it's a random collection, it's independent. And each person would have, that we choose, would have a 10% chance of being left-handed. So the expected number in class would be, of left-handed people, would be n times p. That's our mean. So we'd have 26 times 0.1, which would give us 2.6. The standard deviation, we would take the square root of 26 times 0.1 times our q, 0.9. So our standard deviation, if we rounded 2 decimal places, would be 1.53. So to get the range of usual values, we would take 2.6, our mean, minus 2 times the standard deviation, so minus 2 times 1.53. Sorry, I don't know what I hit there. So negative 0.46, which we know in this case 0 would really be our lowest that we could have. So 0 would not be unusual. Up to our higher number will be the mean plus 2 standard deviations. So there we'd get 5.66. So anywhere between 0 and 5 people would be okay. So is our class within the normal range? Well, since we're not actually sitting in a class, that's hard to tell. Would it be unusual if just one person? Well, no, because 1 is between 0 and 5. Would it be unusual if 6 persons? In this case, yes, because 6 is bigger than the 5.66. Okay, we're going to look at another situation here. So it says couples are trying to pre-select baby gender. So couples are trying to get pregnant with a certain, using IVF and making sure they get a girl. So it says in a test of couples trying to have baby girls using the microsort method, 175 of the babies were girls. So now if no method were used and the babies were born randomly, so if we're just talking about nature, not doing it with this microsort method, we're talking about the trials, we've got 300 babies. Our probability of having a girl would just be 0.5. And our Q, so the probability of not having a girl, would also be 0.5. So the mean would be 300 times 0.5, which would give us 150. And our standard deviation would be 300 times 0.5 times 0.5. So we'd get 8.66. So our usual range will do the mean minus 2 standard deviations. So 150 minus 2 times 8.66. So 132.68 up to our highest value would be mean plus 2 standard deviations. So 167.32. So is 175 the results I got unusual for random? And the answer would be yes, because it's bigger than this 167. So what can we conclude? We can conclude this method is working. That it is providing a better chance of having more girls, because just randomly it would be very unusual to get 175 out of 300 babies being girls. Okay, so our last situation here, it says in a past presidential election, the actual voter turnout was around 61% of those eligible to vote. I should say that this is not real data from anything, our current election. In a survey of a sample of 1,000 eligible voters were asked if they voted, and 688 said they did. So if 1,000 people were chosen at random, would this random situation suggest a binomial distribution? So we're doing a survey of 1,000 voters, and we know that 61% of people voted, so the probability of someone voting would be 0.61. Q would be 1 minus 0.61. So we'd have 0.39. So our mean for the situation, we would take 1,000 times 0.61, which would give us 610. Our sigma, we're going to take 1,000 times 0.61 times 0.39. So we get 15.42. So just like we've done in the other problems, to find our range, we're going to take our mean, 610 minus 2 times the standard deviation. So our lower value here would be 579.16, and our largest value we'll add 2 standard deviations, so 640.84. So is 6088 out of the 1000 within the usual range? And the answer is no. That would be unusually large for that town. And so what we might conclude is that some of the people who said they were voting were actually lying. You know, they didn't want to tell people that they didn't vote. So that could be one conclusion. Now, another conclusion is this is just a very politically active town. So there could be different conclusions, and you wouldn't want to jump to any of them. There would be more information, but we would see that something unusual was going. Oh, sorry. So the conclusion, I thought this was voter turnout for everyone, but this was just for the town. So we can probably cross off that conclusion. So what we could probably conclude is some people said they voted when they actually didn't.